So what is this thing we're talking about, impedance? Well, it's a resistance to flow of energy down the transmission line. At low frequencies, all you see is the bulk R that is associated with whatever your conductors are. And that turns out to be a pretty small number and very, very low in the planes and quite low in the traces. When we go away from zero frequency, we notice a couple of parasitics that were there all the time but were not visible at DC, namely inductance that's along the length of the transmission line, capacitance between the transmission line and the rest of the world. In audio frequencies, those two take over the behavior of a transmission line. And we'll discover that we can figure out what the impedance is by knowing what the R per unit, L per unit length is and the C per unit length. If you're struggling with what this impedance business is all about, Eric wrote a really good article in printed circuit design in January 2000. It's SE is Speeding Edge. It's on my website. You can download it if you are struggling with this whole concept. I did to start with. How can I was taught in technician school that the wires are short circuits, so the voltage is the same at both ends. Well, not quite. How can they be different at both ends? And it's the parasitics along the path that are doing that. So this is a different reflection equation. It is based on the fact that you and I have nifty little tools that let us measure the impedance of transmission lines. And so Z sub L is the impedance downstream from a transition, and Z0 is upstream. If the end of the line is an open circuit, meaning Z sub L is infinity, then we have infinity over infinity, and that says that 100% of the energy will reflect off that open circuit, and the polarity will be positive. And the other extreme is if it's a short circuit, meaning Z sub L is 0, then this is -1, and then we still reflect all the energy back, but now it's inverted.